Hello, dear wanderer. Welcome back to the Midnight Explorer, where we drift together through the quiet corridors of wonder, where stories unfold like constellations in the velvet dark. Tonight, settle yourself comfortably. Perhaps you're tucked beneath warm blankets or sitting by a window where the night sky stretches endlessly above. Wherever you are, take a slow breath. Let the day's noise fade away like distant thunder. Tonight, we journey not through forests or forgotten cities, but upward, into the infinite cathedral of space itself. We're going to explore the cosmic mysteries that have haunted humanity since the first human looked up and wondered, what is all this? Where did it come from? And what secrets hide in the darkness between the stars? This is not a story of facts and figures alone, though those will come. This is a story of longing, of curiosity, of the persistent human need to reach beyond ourselves and touch the face of eternity. It's a story that began thousands of years ago beneath desert skies and continues tonight as you listen to these words suspended on this small blue world in the vastness of everything. So let us begin our journey. Close your eyes if you wish. Let my words paint pictures in the darkness of your mind. And together, we'll travel to the edge of understanding itself. Are you ready? Then let us explore. The air is cool and sharp, carrying the scent of ancient grasses and distant rain. A small band of humans sits around a fire that crackles and pops, sending sparks spiraling upward into the darkness. The flames cast dancing shadows on their faces, faces not so different from yours or mine. They have the same eyes, the same capacity for wonder. One of them, let's call her Ayana, though of course we cannot know her name, feeds another branch into the fire. The wood is dry and catches quickly, and as the flames leap higher, she looks up. And there it is, the night sky. But not the night sky you know from your backyard or even from a camping trip far from city lights. This is a sky unpolluted by the glow of human civilization. This is the sky as it was meant to be seen, a river of light pouring across the darkness so dense with stars that it looks like someone spilled milk across the heavens. Ayana has seen this sky every clear night of her life, yet it never fails to stir something deep within her chest, a feeling she has no words for. Awe, longing, a strange homesickness for a place she's never been. What are those lights? Her people have stories, passed down through generations in the musical cadence of their language. The stars are ancestors watching over them. The stars are campfires of people in the spirit world. The stars are holes poked in the fabric of the night through which the light of day shines through. These stories are beautiful. They are necessary. They help make sense of a world that is vast and often frightening. But even as Ayana recites these stories to her children, even as she believes them with the deepest part of herself, another part of her mind wonders, but what are they really? This question, this simple, profound, dangerous question, is the seed from which all human understanding of the cosmos would eventually grow. Let us drift forward now, through the river of time. Watch civilizations rise like flowers blooming in fast motion. Watch cities emerge from the dust, temples reaching towards the heavens, monuments aligned with perfect precision to the movements of celestial bodies. 5,000 years ago, on the banks of the Nile, Egyptian priests stand on temple rooftops watching the sky with an intensity that borders on religious devotion because for them it is religious devotion. They track the movement of Sirius, the dog star, knowing that its heliacal rising, its first appearance in the dawn sky after a period of invisibility, signals the coming of the Nile's flood, the annual event upon which all Egyptian civilization depends. These priests understand something profound. The sky is not random. It moves with pattern and precision. It can be predicted. And if it can be predicted, it can be understood. In Babylon, centuries later, astronomers climb ziggurats under moonlight, clay tablets and styluses in hand. They record everything: the positions of planets, the phases of the moon, the appearance of comets and meteors. Night after night, year after year, generation after generation, they watch and record. These Babylonian astronomers are meticulous, almost obsessive. They develop mathematical models to predict eclipses with startling accuracy. They divide the sky into constellations and the year into zodiacal signs. They recognize that the movements of celestial bodies follow rules, laws, patterns that transcend the chaos of earthly existence. But here's what moves me most about these ancient astronomers. They knew they would never see the full fruits of their labor. An astronomer might spend his entire life recording planetary positions, knowing that the patterns he sought might only become clear to his grandson's grandson. This was science as an act of faith, as a gift to the future. And halfway around the world, without any contact with the Babylonians or Egyptians, other cultures were doing the same thing. In China, imperial astronomers recorded supernovae, exploding stars, with such precision that modern scientists can match their observations to actual celestial events. In Mesoamerica, the Maya developed calendars of breathtaking complexity and built entire cities aligned to astronomical events. The Polynesians navigated thousands of miles of open ocean using only the stars as their guide. Everywhere humans looked up, they asked questions. Everywhere they asked questions, they found patterns. And everywhere they found patterns, they felt the stirring of something profound. The universe could be understood. The cosmos was not merely chaos. It was a mystery, yes, but a mystery with clues. Now, let us travel to ancient Greece, to a time when philosophy and astronomy were inseparable, when understanding the cosmos was understood as understanding the very nature of reality itself. Picture Pythagoras, walking along a beach at sunset, the waves lapping at his feet. The story goes that he heard the rhythmic clang of blacksmiths' hammers and noticed that certain combinations of strikes created harmonious sounds, while others created discord. This observation, that harmony could be expressed in mathematical ratios, would lead to a revolutionary idea. Perhaps the entire universe was constructed according to mathematical principles. The heavenly bodies, Pythagoras proposed, moved in perfect circles, creating a cosmic harmony as they traveled through the heavens, a music of the spheres too subtle for human ears to perceive, but nevertheless real. The universe, in this view, was not silent, it sang. This idea is beautiful. It's also wrong, at least in its literal interpretation. The planets don't move in perfect circles and they don't create audible harmonies. But Pythagoras was right about something deeper and more profound. The universe does follow mathematical laws. The cosmos is written in the language of mathematics, as Galileo would later observe. Then came Aristotle, standing in his school in Athens, surrounded by students, gesturing upward as he described the heavens as perfect and unchanging, made of a substance different from the corruptible matter of earth. The celestial realm, he taught, operated according to different laws than our earthly realm. For nearly 2,000 years, Aristotle's word would be taken as gospel truth. The idea that Earth and the heavens were fundamentally different would shape not just astronomy, but philosophy, theology, and humanity's place in the cosmos. But even as Aristotle's ideas dominated, other Greek thinkers were pushing in radical directions. Aristarchus of Samos in the 3rd century BCE proposed something almost unthinkable, that Earth was not the center of the universe. Instead, he suggested that Earth and the other planets orbited the Sun. This idea was too radical for its time. It contradicted everything that seemed obvious. When you stand on the Earth, you don't feel it moving. The sun clearly rises in the east and sets in the west, obviously traveling around the Earth. To suggest otherwise felt absurd, like suggesting that up is down or that fire falls instead of rises. So Aristarchus's idea was largely forgotten, buried in the dusty scrolls of history. But ideas, like seeds, can lie dormant for centuries, waiting for the right conditions to sprout.
Let us drift now through what historians once called the Dark Ages, though they were not nearly as dark as that name suggests. In monasteries across Europe, monks copied ancient texts by candlelight, preserving the wisdom of Greece and Rome through centuries of upheaval. In the Islamic world, scholars not only preserved ancient knowledge, but expanded upon it dramatically. In Baghdad, in the House of Wisdom, astronomers built astrolabes of exquisite precision and refined the star catalogues of the Greeks. They gave us many of the star names we still use today: Betelgeuse, Aldebaran, Rigel. These aren't just names, they're a linguistic bridge to a time when Islamic astronomy led the world. Al-Sufi, a Persian astronomer, compiled a book of fixed stars that surpassed anything produced in Europe for centuries. He was the first to observe the Andromeda galaxy, though he couldn't have known what he was seeing. To him, it was simply a little cloud among the stars. Ibn al-Haytham, known in the West as Alhazen, revolutionized optics and developed early versions of the scientific method. He understood that the light we see from stars must travel to reach our eyes. And he wondered, how long does that journey take? This question, how long does light take to travel from the stars, seems simple enough. But embedded within it are the seeds of cosmic mysteries that wouldn't be fully grasped for another millennium. Because when you ask about the speed of light, you're also asking about the nature of time itself. In medieval Europe, the cosmos was imagined as a series of crystalline spheres, nested one within another, like a cosmic set of Russian dolls. Earth sat at the center, unmoving. Around it revolved the moon, then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of fixed stars. Beyond that was the realm of God and the angels. This model was more than astronomy. It was theology. It placed humanity at the physical center of creation, with the heavens literally revolving around us. The model gave the universe a comforting order, a clear hierarchy that extended from the lowliest worm to God himself. But reality, as always, refused to conform to even the most beautiful theories. In 1514, in the Polish city of Frombork, a canon named Nicholas Copernicus sat in his tower room surrounded by books and astronomical instruments, wrestling with a problem. The problem was this: the Earth-centered model of the universe, refined over centuries, had become incredibly complicated. To make the planet's observed motions match the theory, astronomers had to add epicycles upon epicycles upon epicycles. The model worked, after a fashion, but it was inelegant, baroque, almost absurd in its complexity. Copernicus remembered the ancient idea of Aristarchus. What if we put the sun at the center instead? He worked out the mathematics, and to his surprise, everything became simpler. Suddenly, the strange retrograde motion of planets, their occasional backward movement across the sky, made perfect sense. It was just an optical illusion caused by Earth's own motion. But Copernicus was afraid. He was afraid of ridicule from fellow scholars. He was afraid of the theological implications. If Earth was not the center of the universe, what did that mean for humanity's special place in creation? What did it mean for all the biblical passages that spoke of the Earth as fixed and immovable? So Copernicus kept his ideas mostly to himself. He shared them with a few trusted friends. He wrote a manuscript that circulated in small, handwritten copies, and he waited. Only on his deathbed, in 1543 did he finally allow his book, On the Revolutions of the Heavenly Spheres, to be published. Legend says that the printed copy was placed in his hands on the very day he died. He may have touched it. He may have looked at it with fading eyes, this book that would change everything. Or he may have already been beyond such earthly concerns, his mind already traveling to whatever mysteries lie beyond this life. The Copernican revolution, as we now call it, was not immediate. For decades, his model was treated as a mathematical convenience, a useful fiction for calculating planetary positions, not a description of physical reality. But the seed was planted, and seeds, given time and the right conditions, grow. Venice, 1609. The summer air hangs heavy with humidity and the smell of canals. Galileo Galilei, a professor of mathematics in nearby Padua, hears rumors of a new invention from Holland, a device that uses lenses to make distant objects appear closer. Galileo, always fascinated by practical devices, immediately grasps the principle and builds his own version, quickly improving upon the original design. Others have built similar telescopes, but most are using them for terrestrial purposes, spying on distant ships, surveying land, military applications. Galileo does something different. On a clear night, with his hands trembling slightly, whether from excitement or the cool evening air, we cannot know, he points his telescope upward, toward the moon. And everything changes. The moon, which philosophers had assured everyone was a perfect sphere, smooth and unblemished, as befit a celestial body, reveals itself to be covered in mountains and craters. It looks, Galileo realizes with a shock, like Earth. The heavenly realm is not perfect and unchanging. It is made of the same kind of matter as our world. Night after night, Galileo returns to his telescope. He discovers that Jupiter has moons, 4 tiny points of light that change position from night to night. This is profound. Here is direct proof that not everything in the heavens orbits the Earth. Here are worlds orbiting another world. He turns his telescope toward Venus and discovers that it shows phases like the moon, waxing and waning. This is crucial. In the Earth-centered model, Venus should never show a full range of phases, but it does. The Copernican model predicted this. Reality confirms it. Galileo publishes his observations in a little book called Sidereus Nuncio, the Starry Messenger. It becomes an instant sensation across Europe. The heavens are not what we thought. The cosmos is stranger, larger, more wondrous than anyone imagined. But wonder can be dangerous. The Catholic Church, already embattled by the Protestant Reformation, sees Galileo's findings as a threat. In 1633, the elderly Galileo is brought before the Inquisition. Under threat of torture, he recants his support for Copernican theory. Legend says that as he left the courtroom, he muttered, "Eppur si muove," and yet it moves. Whether he actually said those words, we don't know, but they capture something essential. Reality doesn't care about our theories, our beliefs, or our comfort. The Earth moves around the sun regardless of what anyone says. Truth persists, patient and immovable, waiting for us to catch up. Galileo spent his final years under house arrest, forbidden from teaching or publishing on cosmological matters. He went blind before he died, his eyes worn out for years of observations, but he had seen enough. He had glimpsed a larger universe, and that glimpse could never be unseen. England, 1665. The plague sweeps through London, and universities close. A young student named Isaac Newton returns to his family's farm in Woolsthorpe. He's 23 years old, unremarkable in appearance, slender, with long hair, and an intense, penetrating gaze that makes people uncomfortable. Forced into isolation by the plague, with no distractions from his studies, Newton's mind enters a period of almost superhuman productivity. In the space of 18 months, he will lay the groundwork for calculus, make revolutionary discoveries in optics, and solve the greatest cosmic mystery that had vexed astronomers for centuries. What force governs the motion of the heavenly bodies? The story of the apple falling from the tree is probably apocryphal, but it captures something true. Newton wondered, if Earth's gravity can pull an apple downward, how far up does that force extend? To the clouds? To the moon? To the stars? What if, and this was the revolutionary thought, what if the force that makes apples fall is the same force that keeps the moon in its orbit around Earth? What if the heavens and earth are governed by the same laws? Newton worked out the mathematics. The force of gravity, he realized, decreases with the square of the distance. Double the distance, and gravity becomes 4 times weaker. This simple relationship explained everything. In the early 1700s, astronomers using increasingly powerful telescopes noticed fuzzy patches scattered across the night sky. They called them nebulae, from the Latin word for cloud. Some were clearly clusters of stars, but others remained fuzzy and indistinct even under the most powerful telescopes available. What were they? Some astronomers suggested they might be clouds of glowing gas. Others wondered if they might be much more distant than they appeared, perhaps even distant systems of stars, entire other Milky Ways scattered through space. The philosopher Immanuel Kant, in 1755, proposed exactly this, that the nebulae might be island universes, vast collections of stars so distant that they appeared as mere fuzzy patches. It was a stunning idea, but impossible to prove with the technology of the time. Enter William Herschel, a German-born composer who had immigrated to England and developed an obsessive fascination with astronomy. Unable to afford the large telescopes he wanted, Herschel built his own, spending years grinding and polishing mirrors to perfection. On a March night in 1781, while systematically surveying the sky, Herschel noticed something odd, a disc-like object that didn't look like a star. He thought it might be a comet, but as he tracked it night after night, it became clear. This was a new planet, the first planet discovered in recorded history. The 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, had been known since ancient times. Herschel wanted to name it George, after King George III. Thankfully, cooler heads prevailed, and the planet was eventually named Uranus, continuing the tradition of naming planets after Roman gods. The discovery made Herschel famous. More importantly, it gave him the resources to build even larger telescopes. His 40-foot telescope, completed in 1789, was the largest in the world. With it, he began systematically cataloging nebulae and star clusters. Herschel tried to map the shape of the Milky Way itself by counting stars in different directions. He imagined the galaxy as a disc-shaped collection of stars with the sun near the center. He was right about the disc shape, but wrong about our position. We're actually far out in one of the spiral arms, but Herschel had no way of knowing this. After William Herschel's death, his son John Herschel continued the work, traveling to South Africa to survey the southern skies that his father had never been able to observe from England. Between them, the Herschels cataloged thousands of celestial objects and dramatically expanded humanity's map of the cosmos. But the question remained, how big is the universe? Is the Milky Way everything, or is it just one island in an ocean of space? To understand the scale of the cosmos, astronomers first needed to understand something fundamental: the speed of light.
For most of human history, light was assumed to travel instantaneously. You open your eyes and you see. There seemed to be no delay. Galileo actually tried to measure the speed of light by having two people stand on distant hilltops with lanterns, but the speed was far too fast for this method to work. The breakthrough came from an unexpected direction: the moons of Jupiter. In 1676, a Danish astronomer named Ole Romer was carefully timing the eclipses of Jupiter's moons, the moments when they passed behind Jupiter and disappeared from view. He noticed something odd. The eclipses happened earlier than predicted when Earth was moving toward Jupiter, and later than predicted when Earth was moving away from Jupiter. The discrepancy wasn't large, but it was consistent and measurable. Romer realized what was happening. Light takes time to travel from Jupiter to Earth. When Earth is closer to Jupiter, the light has less distance to travel, so we see the eclipses sooner. When Earth is farther away, the light takes longer to reach us. Using the known size of Earth's orbit and the timing discrepancies, Romer calculated that light travels at about 220,000 kilometers per second. This was wrong. The actual speed is about 300,000 kilometers per second, but he was in the right ballpark. More importantly, he had proven that light has a finite speed. This was profound. It meant that when we look at Jupiter, we're not seeing it as it is now, but as it was about 43 minutes ago, the time it takes light to travel from Jupiter to Earth. When we look at the Sun, we see it as it was 8 minutes ago. When we look at the nearest star beyond the Sun, Alpha Centauri, we see it as it was 4.3 years ago. The implication was staggering. When we look out into space, we're looking back in time. The farther we look, the farther back we see. Distance and time become intertwined in a way that feels almost mystical. The light from distant stars began its journey centuries, millennia, millions of years ago. Some of the stars we see might not even exist anymore. They may have died long ago, but their light is still traveling through space, carrying the image of a star that no longer is. This realization gave astronomy a power that few other sciences possess: the ability to directly observe the past. A geologist studying ancient rocks can only infer what the Earth was like millions of years ago. But an astronomer looking at a distant galaxy sees it as it actually was. It's like a time capsule traveling across the void. By the early 1900s, astronomers had powerful new tools at their disposal. Photography allowed them to capture details invisible to the eye. Spectroscopy, the analysis of light broken into its component colors, revealed the chemical composition of stars and their motion toward or away from us. Yet the fundamental question remained: how big is the universe? The Milky Way, that river of light across the night sky, was clearly a vast collection of stars. But were the spiral nebulae, those fuzzy spiral-shaped objects scattered across the sky, part of the Milky Way, or were they separate galaxies, island universes beyond our own? The question came to a head in 1920 in what became known as the Great Debate. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views to the National Academy of Sciences. Shapley argued that the Milky Way was enormous, much larger than previously thought, and that the spiral nebulae were relatively nearby gas clouds within our galaxy. The Milky Way was, in his view, essentially the entire universe. Curtis argued that the Milky Way was smaller and that the spiral nebulae were actually distant galaxies, separate island universes scattered through an incomprehensibly vast space. Both men were partially right and partially wrong. Shapley was right that the Milky Way was much larger than previously thought. He had correctly measured it using variable stars called Cepheids, but he was wrong about the spiral nebulae. Curtis was right that the spiral nebulae were separate galaxies, but he underestimated the size of the Milky Way. The definitive answer came a few years later from a young astronomer named Edwin Hubble working at the Mount Wilson Observatory above Los Angeles. In 1923, using the 100-inch Hooker telescope, then the largest telescope in the world, Hubble photographed the Andromeda Nebula night after night. On one plate, he noticed what appeared to be a nova, a suddenly brightening star. He marked it with an N. But further study revealed it wasn't a nova. It was a Cepheid variable, a type of star whose brightness varies in a regular, predictable way. More importantly, there was a direct relationship between a Cepheid's period of variation and its intrinsic brightness. By measuring how bright the Cepheid appeared and knowing how bright it actually was, Hubble could calculate its distance using the inverse square law. The math was simple, but the implication was staggering. The Cepheid in Andromeda was nearly 1 million light-years away. We now know it's about 2.5 million light-years away. This was far beyond even the largest estimates of the Milky Way's size. Andromeda wasn't part of our galaxy. It was its own galaxy, a vast collection of hundreds of billions of stars, an island universe just as Kant had imagined nearly 2 centuries earlier. Hubble crossed out the N on his photographic plate and wrote VAR for variable star. Then, in his excitement, he added an exclamation point, a rare show of emotion for the usually reserved Hubble. The universe had suddenly become unimaginably larger. If Andromeda was a separate galaxy, then all the other spiral nebulae must be galaxies too. The Milky Way was just one galaxy among countless others, scattered through space like islands in a cosmic ocean. We were not at the center of the universe. We weren't even at the center of our own galaxy. We were inhabitants of one ordinary planet orbiting one ordinary star in the outer reaches of one ordinary galaxy. As he measured the distances to more and more galaxies, he noticed something peculiar. The light from these distant galaxies was shifted toward the red end of the spectrum. Red-shifted, as astronomers called it. This redshift was caused by the Doppler effect, the same phenomenon that makes a train whistle sound higher-pitched as it approaches and lower-pitched as it moves away. Light waves from objects moving away from us get stretched, shifting toward the red end of the spectrum. The galaxies were moving away from us. More than that, Hubble noticed a pattern. The farther away a galaxy was, the faster it was moving away. This relationship became known as Hubble law. What did this mean? At first, it seemed like we must be at the center of some kind of cosmic explosion with galaxies flying away from us in all directions. But that couldn't be right. We'd already learned that we weren't at the center of anything. The answer required a shift in thinking about space itself. Imagine the universe as the surface of a balloon, with galaxies drawn as dots on the balloon surface. As you inflate the balloon, all the dots move away from each other. From the perspective of any dot, all the other dots appear to be moving away, and the farther away a dot is, the faster it appears to recede. Now imagine this in 3 dimensions instead of 2. Space itself is expanding, carrying galaxies along with it. There is no center to this expansion, or rather, every point is equally the center. The Big Bang didn't happen at a location in space. It happened everywhere at once because it was space itself that began expanding. This was hard to wrap one's mind around. It still is. Space isn't just the stage on which cosmic events play out. It's dynamic, expanding, carrying galaxies along like boats on a river. The implications were profound and unsettling. If the universe is expanding now, that means it was smaller in the past. Follow the expansion backward in time, and you reach a point where
everything in the universe, all matter, all energy, all space itself, was compressed into an infinitesimally small point. The universe had a beginning. This idea, initially proposed by a Belgian priest and physicist named Georges Lemaitre, was met with skepticism. Many scientists, including Einstein initially, found it distasteful. An eternal, unchanging universe felt more philosophically satisfying than one with a definite beginning. The British astronomer Fred Hoyle mockingly called it the Big Bang Theory, a term that stuck despite Hoyle's opposition to the idea. But evidence kept accumulating. In the 1940s, physicist Gamow and his colleagues made a startling prediction. If the universe began in a hot, dense state and has been expanding ever since, then the universe should be filled with leftover radiation from that initial fireball, ancient light, stretched and cooled by billions of years of expansion, now appearing as microwave radiation. For 20 years, this prediction went untested. The technology to detect such faint radiation didn't exist yet. New Jersey, 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna, preparing it to detect radio signals from space, but they kept picking up persistent background noise, a faint uniform hiss that came from every direction in the sky. They thought it might be interference from nearby New York City. They thought it might be pigeon droppings inside the antenna, and they did spend time cleaning out what they delicately called white dielectric material. But the noise persisted. Meanwhile, just 37 miles away at Princeton University, a team of physicists led by Robert Dicke was building equipment to search for exactly this kind of radiation, the predicted leftover glow from the Big Bang. When the two groups learned of each other's work, the pieces fell into place. Penzias and Wilson had accidentally discovered what Dicke's team was deliberately searching for: the cosmic microwave background radiation, the oldest light in the universe, the afterglow of creation itself. This radiation is everywhere. Right now, as you're listening to these words, you are bathed in it. If you could see microwave frequencies, you would see a faint glow coming from every direction. Not from stars or galaxies, but from space itself, carrying information about the universe as it was 380,000 years after the Big Bang. Why 380,000 years? Before that time, the universe was so hot and dense that light couldn't travel freely. It would scatter off free electrons after going only a short distance. But as the universe expanded and cooled, there came a moment when electrons combined with protons to form neutral hydrogen atoms. Suddenly, the universe became transparent. Light could travel freely for the first time. That light has been traveling ever since, stretched by the expansion of space from visible light to infrared to microwaves. When we observe the cosmic microwave background, we're seeing the universe at its moment of becoming transparent, a baby picture of the cosmos taken just 380,000 years after its birth. Detailed maps of this radiation, made by satellites like COBE, WMAP, and Planck, reveal tiny temperature variations, regions that were slightly denser or slightly less dense than average. These tiny density variations were the seeds from which all structure in the universe would grow. Galaxies, clusters of galaxies, and the vast cosmic web of matter that threads through the cosmos. From these observations, we've learned the age of the universe, 13.8 billion years, its composition, and its ultimate fate. The cosmic microwave background is one of the most important discoveries in the history of astronomy, a direct connection to the birth of everything. Penzias and Wilson received the Nobel Prize in 1978, but in some ways, the real prize was the knowledge itself, confirmation that the universe had a beginning, that we could observe and measure that beginning, and that the cosmos tells us its own story if we know how to listen. But even as the picture of the universe seemed to be coming together, new mysteries emerged, mysteries so profound they challenged everything we thought we understood. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies bound together by gravity. By measuring how fast the galaxies were moving, he could calculate how much mass the cluster must contain to hold itself together gravitationally. The answer shocked him. The visible matter, all the stars and all the galaxies, couldn't account for more than a small fraction of the gravitational pull. There wasn't enough visible matter to prevent the cluster from flying apart. Yet there it was, held together by gravity. Something invisible was providing most of the gravitational pull. Zwicky called it dunkel Matter, dark matter. The idea was largely ignored for decades, but in the 1970s, astronomer Vera Rubin made similar observations while studying the rotation of spiral galaxies. Stars at the outer edges of galaxies were moving far too fast. Based on the visible matter alone, they should have been flung out into intergalactic space. Something invisible was holding them in place. Study after study confirmed the same result. Galaxies and clusters behave as if they contain far more matter than we can see. This dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. It interacts only through gravity. And it's everywhere. In fact, calculations suggest that dark matter makes up about 85% of all matter in the universe. The stars, planets, gas clouds, and nebula, everything we can see, everything that we think of as normal matter, is just a tiny fraction of what's actually out there. Think about that for a moment. Everything we've ever seen with our eyes or our telescopes, everything we've ever touched or measured, all the matter that makes up our bodies and our world, all of it represents less than 5% of the total contents of the universe. The rest is hidden. We know it's there because we can see its gravitational effects, like seeing wind by watching leaves blow, but we can't detect it directly. We don't know what it's made of. Physicists have proposed various candidates, exotic particles with names like WIMPs and axions. But so far, all attempts to detect dark matter particles directly have come up empty. It's humbling. After centuries of progress, of unveiling cosmic secrets one by one, we discover that the vast majority of the universe is made of something we can't see and don't understand. But wait, it gets stranger. In the 1990s, two teams of astronomers set out to measure the deceleration of the universe's expansion. Everyone knew the universe was expanding, but gravity should be slowing that expansion down. The question was, how much? To answer this, they studied Type 1a supernovae, exploding stars that serve as standard candles, because they all reach roughly the same peak brightness. By measuring how bright they appear, you can calculate how far away they are, and by measuring their redshift, you can determine how fast they're moving away from us. The teams expected to find that the expansion was slowing down. What they found instead was shocking. The expansion is speeding up. Let me repeat that. The expansion of the universe is accelerating. Not only are distant galaxies moving away from us, but they're moving away faster and faster as time goes on. This made no sense. Gravity is attractive. It should be pulling everything together, or at least slowing that expansion down. What could possibly be pushing the universe apart with ever-increasing force? The answer, according to our best theories, is something called dark energy. And just like dark matter, we have no idea what it actually is. Dark energy appears to be a property of space itself. As space expands, more space is created, and with it, more dark energy. This creates a kind of cosmic feedback loop. Dark energy causes space to expand faster, which creates more space, which contains more dark energy, which causes even faster expansion.
According to our current observations, dark energy makes up about 68% of the universe. Add in dark matter at 27%, and normal matter, everything we can see and touch, accounts for just 5% of the universe. We live in a universe where 95% of everything is invisible and mysterious. Dark matter holds galaxies together, dark energy tears the universe apart, and in between these opposing forces, in the narrow space where gravity and expansion balance, we find the conditions necessary for stars, planets, and life. The implications for the far future are sobering. As dark energy continues to accelerate the expansion, galaxies beyond our local group will eventually recede so fast that their light will never reach us. Billions of years from now, an observer in the Milky Way would see a much emptier universe, just our own galaxy and the few others gravitationally bound to us, surrounded by darkness. Eventually, even the stars will burn out. The universe will grow cold and dark. This is sometimes called the heat death of the universe, not a dramatic explosion, but a slow fade into darkness and cold. But that's trillions of years away. For now, we exist in a special time, when the universe is old enough for complex structures to form, but young enough that stars still burn brightly and galaxies still fill the sky. Let us turn now to one of the most mysterious and captivating objects in the cosmos: black holes. The story begins, oddly enough, with Einstein's general theory of relativity, published in 1915. Einstein showed that gravity isn't a force pulling objects together, but rather a curvature of space-time itself. Mass warps the fabric of space and time, and objects follow the curves created by that warping. Just months after Einstein published his equations, a German physicist named Karl Schwarzschild found an exact solution to those equations, a solution describing what happens around a point of infinite density. At a certain distance from this point, called the event horizon, space becomes so warped that nothing, not even light, can escape. Einstein himself found this result disturbing and didn't believe such objects could actually exist in nature. They seemed too extreme, too bizarre. But nature, as always, is more imaginative than we are. In 1931, astrophysicist Subramanian Chandrasekhar, then just 19 years old, was sailing from India to England to begin his graduate studies. During the voyage, he worked through some calculations and made a startling discovery. When a star more than 1.4 times the mass of the Sun runs out of fuel, nothing can stop its collapse. The star will compress itself into an infinitely dense point. This was the first theoretical prediction of what we now call black holes, although the term wouldn't be coined until 1967 by physicist John Wheeler. For decades, black holes remained mathematical curiosities, but in the 1960s, astronomers began discovering X-ray sources in space, regions emitting enormous amounts of high-energy radiation. One of these, Cygnus X1, showed peculiar behavior. It seemed to be a binary system where visible matter from a normal star was being pulled into something invisible and incredibly massive. The evidence pointed to a black hole, a region of space where gravity is so intense that space-time itself is torn. At the event horizon, time essentially stops from an outside observer's perspective. If you could watch someone fall into a black hole, you'd see them slow down, becoming redder and dimmer, frozen at the edge forever. But from the falling person's perspective, they'd cross the horizon in finite time, unaware of anything special about that boundary. Beyond the event horizon lies the singularity, a point where density becomes infinite and the laws of physics as we know them break down. We can't observe singularities directly. They're hidden behind the event horizon, veiled by what physicists call cosmic censorship. In 2019, we got our first direct image of a black hole, or rather, its shadow. The Event Horizon Telescope, a network of radio telescopes spread across the globe, created an Earth-sized virtual telescope and pointed it at M87, a supermassive black hole at the center of a distant galaxy. The image showed exactly what Einstein's equations predicted, a ring of light surrounding a dark circular shadow. The light comes from superheated matter swirling around the black hole just outside the event horizon.
The shadow is the black hole itself, an absence where light cannot escape. It was a moment of profound beauty and vindication, seeing at last direct evidence of one of the universe's most exotic predictions. Black holes are real. Space and time can be torn, and Einstein, despite his own doubts, was right. At the center of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, millions or even billions of times more massive than the Sun. These aren't just cosmic oddities, they play a crucial role in galaxy formation and evolution, regulating star formation through their powerful jets and winds. Our galaxy's central black hole, called Sagittarius A, has a mass of about 4 million suns. It's relatively quiet right now, only occasionally snacking on nearby gas or an unlucky star, but we've observed the orbits of stars around it, watching them whip around at thousands of kilometers per second, their paths precisely following the curves predicted by general relativity. Black holes represent the ultimate cosmic mystery, places where our understanding breaks down, where the fabric of reality is stretched to its breaking point. They are both endings and beginnings, destroying everything that falls into them, while possibly giving birth to new universes in ways we don't yet understand.
For thousands of years, humans have wondered, are there other worlds like Earth? Other planets? Perhaps even other life? Until recently, we could only speculate. We knew our solar system contained other planets, but they were clearly inhospitable. Mercury, too hot; Venus, a hellish greenhouse; Mars, a frozen desert; the gas giants, utterly alien. The question of planets around other stars was even more difficult. Stars are so distant and so bright that seeing a planet next to one is like trying to spot a firefly next to a lighthouse from miles away. But in 1995, everything changed. Swiss astronomers Michel Mayor and Didier Queloz detected a planet orbiting a sun-like star called 51 Pegasi. They detected it not by seeing it directly, but by observing the tiny wobble it induced in its parent star as it orbited. The planet they found was shocking, a gas giant larger than Jupiter, orbiting its star once every 4.2 days, far closer than Mercury orbits our sun. This hot Jupiter shouldn't exist according to our theories of planetary formation, yet there it was. The floodgates opened. Within a few years, dozens of exoplanets were discovered. Within 2 decades, thousands. As I speak to you now, we've confirmed over 5,000 exoplanets, with thousands more awaiting confirmation. They come in stunning variety: super-Earths twice our planet's size, mini-Neptunes, lava worlds with surfaces hot enough to melt iron, water worlds covered in deep oceans, rogue planets drifting through interstellar space untethered to any star. In 2009, NASA launched the Kepler Space Telescope, designed specifically to find Earth-like planets in Earth-like orbits. For 4 years, it stared at a single patch of sky, monitoring 150,000 stars, watching for the tiny dimming that occurs when a planet crosses in front of its star. Kepler's discoveries revolutionized our understanding. Rocky planets are common. Many stars have multiple planets. And here's the stunning conclusion: there are likely more planets in the Milky Way than there are stars. Planets aren't the exception, they're the rule. Some of these planets orbit in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Water, as far as we know, is essential for life. And if water is possible, then perhaps life is too. The discovery of exoplanets has transformed the ancient question, "Are we alone?" from philosophy to science. We now have actual planets to study, atmospheres to analyze, potential homes for life to investigate. We've even begun to analyze the atmospheres of these distant worlds. When a planet crosses in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths of light, leaving chemical fingerprints we can detect. So far, we haven't found definitive signs of life, But we're only beginning. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect biosignatures, chemical signs of life, in the atmospheres of nearby planets. Gases like oxygen, methane, and others, present in certain combinations, could indicate biological processes. Within the next decade or two, we might know if we're alone. We might find evidence of life beyond Earth, perhaps just microbial life, but life nonetheless. This would be one of the most profound discoveries in human history, answering a question we've asked since we first looked up at the stars. But there's another, more unsettling possibility. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to UFOs and alien life. Fermi suddenly asked a simple question: where is everybody? His point was this: the Milky Way is ancient, over 13 billion years old. It contains hundreds of billions of stars. Many of these stars are older than our Sun. If intelligent life is common, then even given the vast distances between stars, an advanced civilization should have had plenty of time to colonize the entire galaxy. So where are they? Why haven't we seen any evidence of alien civilizations? Why is the sky so silent? This became known as the Fermi paradox, and it has haunted astronomers and philosophers ever since. Various solutions have been proposed. Perhaps intelligent life is exceedingly rare. Maybe we're the first, or one of the first, civilizations to arise in the galaxy. Perhaps there's a great filter, some extremely difficult step in the evolution of complex life that most species never pass. The unsettling question: is the filter behind us or ahead of us? Perhaps advanced civilizations inevitably destroy themselves through war, environmental collapse, or some technological catastrophe we can't even imagine. Perhaps they're out there, but choose not to reveal themselves. Perhaps they're so different from us that we wouldn't recognize their signals or artifacts as artificial. Or perhaps the distances are simply too vast. Even traveling at a significant fraction of light speed, crossing the galaxy would take tens of thousands of years. Maybe civilizations arise, flourish, and fall without ever making contact with each other. Islands of consciousness separated by gulfs too vast to bridge. In 1960, astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars, listening for artificial signals. He heard nothing but natural radio noise. This was Project Ozma, the first modern search for extraterrestrial intelligence. SETI. Since then, SETI projects have surveyed millions of star systems, listening across broad swaths of the radio spectrum. The search has expanded to include optical SETI, looking for brief laser pulses, and technosignature searches, looking for signs of alien engineering or industry. So far, silence. But absence of evidence isn't evidence of absence. We've only searched a tiny fraction of the sky, at a limited range of frequencies for brief periods of time. The galaxy is vast, and radio signals weaken with distance. A civilization just 100 light-years away might be shouting into the cosmos, and we might simply not have heard them yet. There's also the question of what we're looking for. We search for radio signals because that's our technology, but an advanced civilization might use communication methods we haven't even imagined. Looking for radio signals might be like trying to find modern humans by searching for smoke signals. Some scientists have suggested searching for megastructures, vast engineering projects that would be visible across interstellar distances. A Dyson sphere, for instance, a shell built around a star to capture all its energy, would create a characteristic infrared signature. So far, we found some intriguing candidates, but nothing conclusive. The search continues, and every negative result tells us something. If we don't find life, that makes our existence even more precious. We might be the only eyes through which the universe observes itself, the only consciousness arising from matter in all this vast ancient galaxy. That's a profound responsibility.
Einstein's general relativity predicted something extraordinary. Violent cosmic events should create ripples in space-time itself. Gravitational waves, spreading outward at the speed of light like ripples on a pond. For a century, these remained purely theoretical. The effect is so tiny that detecting them seemed nearly impossible. Einstein himself thought they could never be measured. But physicists are stubborn. In the 1960s and 70s, pioneers like Joseph Weber tried to detect gravitational waves using massive metal cylinders. Weber claimed success, but his results couldn't be reproduced. A more sophisticated approach was needed. In the 1990s, construction began on LIGO, the Laser Interferometer Gravitational Wave Observatory. Two L-shaped facilities, one in Louisiana and one in Washington state, each with arms 4 kilometers long. The principle is elegant. Laser beams travel down both arms and bounce back. Normally, the beams return at exactly the same time. But if a gravitational wave passes through, it stretches space in one direction while compressing it in the other. The beams return slightly out of sync, incredibly slightly. LIGO was designed to detect changes smaller than 1,000th the width of a proton. For years, nothing. Just the background rumble of Earth itself. Trucks driving past, ocean waves hundreds of miles away, even the quantum jitter of the atoms in the mirrors. Then on September 14, 2015, at 5:51 a.m. Eastern Time, both detectors registered an unmistakable signal. A chirp, rising in frequency and amplitude before cutting off abruptly. The signal matched perfectly what theory predicted from two black holes spiraling together and merging. The black holes, each about 30 times the mass of the Sun, had been orbiting each other for billions of years, gradually spiraling inward. In their final fractions of a second, they reached incredible speeds, a significant fraction of light speed, before merging into a single, larger black hole. The collision released more energy than all the stars in the visible universe combined, but not as light, as gravitational waves. Those waves traveled across 1.3 billion light-years of space before passing through Earth, causing the mirrors in LIGO to move by less than the width of a proton. And we detected it. We felt space-time itself ripple. This wasn't just a confirmation of Einstein's theory. It was the opening of a new window on the universe. For all of human history, we've learned about the cosmos through electromagnetic radiation, visible light, radio waves, X-rays, and so on. Gravitational waves are something completely different. They're not radiation traveling through space, they're distortions of space itself. Since that first detection, dozens more gravitational wave events have been observed. Most are black hole mergers, but some are collisions between neutron stars, the ultra-dense remnants of massive stars. One neutron star collision, detected in 2017, was also observed with traditional telescopes. This multi-messenger astronomy, observing the same event with both gravitational waves and light, revealed that neutron star collisions are the forges where heavy elements like gold and platinum are created. The gold in your jewelry, the platinum and catalytic converters, the iodine in your body, all of it was created in the violent collision of neutron stars billions of years ago, scattered into space, incorporated into the cloud that would eventually form our solar system, and finally finding its way to Earth. Gravitational wave astronomy is still in its infancy. More sensitive detectors are being built. Future space-based detectors will detect waves from even more massive events. We're learning to listen to the universe in a new language, not the language of light, but the language of space-time itself.
Let us venture now into more speculative territory, to ideas that push against the boundaries of science and philosophy. The multiverse. The idea is simple but staggering. What if our universe, everything we can observe, all 93 billion light-years of visible space, is just one bubble in an infinite foam of universes? This isn't idle speculation. Several well-regarded physical theories lead, somewhat reluctantly, to the multiverse conclusion. One route comes from inflation theory. In the first fraction of a second after the Big Bang, space expanded exponentially fast, faster than light, driven by a field called the inflaton. This rapid inflation smoothed out irregularities and explains why the universe looks roughly the same in all directions. But according to our best models, inflation doesn't happen just once. It's happening constantly, eternally, in different regions of space. Our universe is a region where inflation stopped, allowing matter and galaxies to form. But beyond our cosmic horizon, inflation continues, spawning endless other bubble universes. These universes might have different physical laws, different constants of nature. The strength of gravity, the mass of electrons, the speed of light. Everything we think of as fundamental might just be local bylaws in our particular cosmic neighborhood. Another route to the multiverse comes from quantum mechanics. In the standard interpretation, when a quantum system is measured, it collapses into one state. But in the many worlds interpretation, proposed by physicist Hugh Everett, the universe splits into multiple branches, one for each possible outcome. Every quantum event, and there are countless quintillions happening every second, creates new universes. Right now, there are universes where you made different choices, where history unfolded differently, where the constants of physics vary slightly or dramatically. Then there's the mathematical multiverse, proposed by physicist Max Tegmark. His idea, if a universe can be described by mathematical structures, and all consistent mathematical structures exist in some sense, then all possible universes exist. These ideas strain credulity. They seem to violate Occam's razor, the principle that we shouldn't multiply entities unnecessarily. One universe seems complicated enough without invoking infinite more. But here's the thing. Science doesn't care about our comfort or intuition. If the multiverse is a logical consequence of our best theories, we have to take it seriously even if it seems absurd. There's also something called the anthropic principle at play here. The constants of nature in our universe seem finely tuned for life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all. The strong nuclear force, the cosmological constant, the masses of fundamental particles, change any of these by even a small amount, and you get a universe incapable of supporting life. Some see this as evidence of design, but the multiverse offers an alternative explanation. If there are infinite universes with varying constants, then inevitably some will have the right conditions for life. We find ourselves in one of those universes simply because we couldn't exist in the others. It's selection bias on a cosmic scale. The question of whether the multiverse exists might be fundamentally unobservable. If other universes are forever beyond our cosmic horizon, causally disconnected from us, can we ever confirm they exist? Some physicists argue that the multiverse is therefore unfalsifiable and thus not proper science. Others counter that if a theory makes predictions we can test in our universe, and that theory logically requires a multiverse, then we have indirect evidence for the multiverse. The debate continues. But regardless of whether the multiverse exists,
The fact that our best theories lead us there tells us something important. Reality is likely far stranger and more vast than our everyday experience suggests.
Among all the cosmic mysteries, perhaps none is more intimately familiar yet fundamentally baffling than time itself. We experience time as flowing in one direction, from past to future. We remember yesterday, but not tomorrow. We can influence the future, but not the past. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. This directionality, the arrow of time, seems obvious, fundamental. But here's the mystery. The fundamental laws of physics don't distinguish between past and future. Newton's laws work equally well if you run time backward. So do Maxwell's equations of electromagnetism. Even Einstein's relativity is time-symmetric. At the most fundamental level, physics says that time could flow either direction, yet our experience says otherwise. Why? The answer involves something called entropy. Loosely speaking, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases in closed systems. Order decays into disorder. Organized energy dissipates into random heat. This is why eggs break, why coffee cools, why we age. But why should entropy increase? The answer traces back to probability. There are far more ways for a system to be disordered than ordered. If you shuffle a deck of cards, it's fantastically unlikely to end up in perfect order. Not impossible, just improbable beyond measure. The early universe, for reasons we don't fully understand, had extremely low entropy. It was highly ordered, with all matter and energy distributed smoothly. As the universe evolved, entropy increased. Matter clumped into stars and galaxies. Stars burned, producing heat. Energy became more and more disordered. This entropy increase creates the arrow of time. The future is the direction in which entropy increases. Our memories form in this direction because memory formation is an entropy-increasing process. We can remember the past because the past was lower entropy. We can't remember the future because it's higher entropy. But this raises a profound question. Why was the early universe in such a low entropy state? Why did things start out so ordered? One possibility, it was just incredibly unlikely, a statistical fluke. We exist to observe it precisely because it happened. Another possibility, the Big Bang itself somehow necessitated low initial entropy through mechanisms we don't fully understand. A third possibility, time didn't actually begin at the Big Bang. Perhaps the universe existed in some form before, went through a big crunch, then bounced into a new Big Bang. Or perhaps our universe budded off from a previous universe through a black hole singularity. The physicist Sean Carroll has proposed that time might be symmetrical on the grandest scale. Our universe is expanding and increasing in entropy, yes, but perhaps far in the future, or in other bubble universes, time runs the other way, with entropy decreasing. From a God's eye view outside time, the multiverse might be timeless, with different regions experiencing time flow in different directions, each region thinking its direction is the only one. These ideas push against the limits of what we can meaningfully say. Time is so fundamental to our existence that questioning it feels like questioning reality itself. And perhaps that's appropriate, because the more we understand about the universe, the more we realize that reality is not what it seems. Space is not a passive stage, but a dynamic entity. Time is not absolute, but relative. Matter is not solid, but mostly empty space. Energy and matter are interchangeable. Particles can be in multiple places at once until observed. The universe is queerer than we suppose, queerer perhaps than we can suppose.